Welcome to this video on nuclear equations, a key topic in your GCSE Physics revision of atomic structure. In this video, we will cover the basics of nuclear equations, explore alpha and beta decay, discuss how to balance these equations, and look at the unique characteristics of gamma decay. Radioactive decay is the spontaneous process where an unstable nucleus releases energy or particles to become more stable. Nuclear equations represent this mathematically, showing the changes in the nucleus. Just like in chemistry, these equations must be balanced. To balance these equations, we use nuclide notation. The mass number, A, is the total number of protons and neutrons at the top left. The atomic number, Z, is the number of protons at the bottom left. For example, in carbon-14, the top number, 14, is the mass number, while the bottom number, 6, is the atomic number. You can find the number of neutrons by subtracting the atomic number from the mass number. The golden rule for nuclear equations is the conservation of mass and charge. Both the total mass number and the total atomic number must be equal on both sides of the equation. Alpha decay occurs when a nucleus emits an alpha particle, which is identical to a helium-4 nucleus containing 2 protons and 2 neutrons. In alpha decay, the mass number decreases by 4, and the atomic number decreases by 2 as the emitted alpha particle takes those away. Here is an example using uranium 238. Notice how the parent nucleus decays into a daughter nucleus and an alpha particle, with the mass and atomic numbers perfectly balanced on both sides. To write an alpha decay equation, follow these steps. Identify the parent, note the alpha particle, calculate the new daughter nucleus, and verify the balance. Let's walk through radon 222. By subtracting the mass and atomic numbers of the alpha particle, we find the resulting polonium-218 daughter nucleus. In beta decay, a neutron inside the nucleus converts into a proton and an electron. This high-energy electron is then ejected as a beta particle. During beta decay, the mass number remains unchanged because the total number of nucleons is the same. However, the atomic number increases by 1. Using carbon-14 as an example, the beta particle is written with a mass of 0 and an atomic number of -1, showing the balance is maintained after the electron is emitted. For beta decay, follow these steps. Identify the parent nucleus, note the beta particle as 0 and -1, calculate the new atomic number, and confirm the balance. Let's look at a worked example for beta decay. Strontium-90 has an atomic number of 38. When it undergoes beta decay, the atomic number increases by 1 to 39, identifying the daughter nucleus as yttrium. Gamma decay is fundamentally different. Instead of emitting a particle, the nucleus releases a high-energy gamma-ray photon to drop to a lower energy state. Because gamma radiation has no mass and no charge, the nucleus remains unchanged in composition. The mass and atomic numbers stay exactly the same. This table summarizes the changes for alpha, beta, and gamma decay. Notice how alpha decay significantly changes the nucleus, while gamma decay does not change the element at all. We balance nuclear equations because of 2 fundamental laws: the conservation of mass energy and the conservation of charge. These ensure the physics remains consistent. To master balancing equations, follow these 4 steps. Write down the parent nucleus, identify the emitted particle, calculate any unknowns, and verify the final balance. When you encounter an unknown in an equation, add the known mass and atomic numbers on both sides. The difference between these totals identifies your missing particle or nucleus. Common mistakes to watch for. Don't forget the alpha particle notation. Be careful with the positive and negative signs in beta decay, and always check both numbers. Now for some practice. Try this. polonium 210 undergoes alpha decay. Can you write the equation and identify the daughter nucleus? Checking the math for polonium, 210 minus 4 gives a mass of 206, and 84 minus 2 gives an atomic number of 82. This identifies the daughter as lead. Let's try one more. Iodine 131 undergoes beta decay. Can you identify the resulting daughter nucleus? For the iodine beta decay, the mass stays 131, but the atomic number increases to 54. This identifies the daughter nucleus as xenon. Here is a challenge. Look at this radium decay equation. By examining the change in mass and atomic number, we can deduce that this is alpha decay. Nuclear equations have real-world uses, from carbon dating ancient artifacts to precision medical treatments and generating electricity in nuclear power plants. Thank you for watching this guide on nuclear equations. Keep practicing these steps, and you'll be well prepared for your exams. The periodic table is an essential tool for balancing nuclear equations. When you calculate the atomic number of a daughter nucleus, you use the table to identify the specific element. Gamma decay rarely happens alone. It usually follows alpha or beta decay. When a daughter nucleus is in an excited energy state, it releases a gamma ray to stabilize without changing its proton or neutron count. In equations, gamma radiation is represented by the Greek letter gamma. Because it is electromagnetic radiation rather than a particle, it has no mass and no charge, meaning it doesn't affect the balance of your equation. For quick revision, remember these values. An alpha particle has a mass of 4 and 2 protons. A beta particle has a mass of 0 and a charge of -1. Many heavy elements don't reach stability in one step. They undergo a decay series, a chain of successive alpha and beta decays, until they eventually become a stable isotope, like lead-206. When answering exam questions, follow these 4 steps. Carefully read the prompt, list all known values, apply the conservation rules to balance the equation, and identify the final element. Here's a brief glossary of key terms to master: mass number, atomic number, alpha and beta particles, gamma rays, daughter nuclei, and the standard format for nuclide notation. Keep these top tips in mind. Always balance both mass and atomic numbers. Remember the specific notation for alpha and beta particles, and note that gamma decay changes nothing in your equation. Use the summary visual to quickly review how different decay types affect the mass and atomic numbers of the nucleus. You are now ready. We have covered the core concepts of nuclear equations. Remember to practice your balancing, use the periodic table provided, and check your work carefully in the exam.